Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 5 of a unit moving charges and magnetism. So let's begin with today's class. In today's class, we are going to discuss about the applications of Biot-Savart law. We have already done with the application that is magnetic field due to straight finite or infinite length current carrying conductor. We have discussed that. In today's class we are going to discuss about the magnetic field due to a circular charged arc on its axis. So let's begin. As you can see in the figure, a circular ring is given, and that ring is carrying a current I, and the radius of the ring is the r. On its axis, on the axis of the ring, a certain point P is there, and on point P my requirement is to find out the magnetic field. So what I can do is that I have chosen one of the segment, it's an IDL, and from there I have make a position vector that makes an angle theta over here, and this is the direction of the dB that I have find it out using the right hand screw rule. Yes, so this is the direction of the magnetic field. If I choose this as a theta, then this could be the dB cos theta, and if this is dB cos theta, this is dB sin theta. If I choose the another segment, let's suppose over here, then its dB cos theta will be in this direction, and its dB sin theta would be in this direction. That means I hope you understand that this dB cos theta, this dB cos theta, and this dB cos theta, these two are going to cancel out each other. And if they are going to cancel out each other, that means only the sin theta component will remain. So what I have done is the total magnetic field should be is equals to integration of dB sin theta. Now what is dB at that point? It's a mu naught by 4 pi into IDL by r square into sin theta, that we understand. So let's just integrate this. Let's just integrate this by having a value of sin theta. If you can see the triangle very carefully, this is 90 degree, this is angle theta, then this sin theta could be written as sin theta could be replaced as the r divided by r. Yes, so if sin theta is equals to r by r, this is equals to mu naught by 4 pi IDL r square multiplied by r by r, where small r stands for under root of r square plus x square, where r is the radius of the ring and x is the axial distance from the center to point P. So this is mu naught I r upon 4 pi r cube integration of dl. If I take this as a small segment and if I integrate this over complete ring, let's suppose if I integrate this situation over a complete ring, something like this, then this integration will give me a 2 pi r. I hope this is clear. If this is clear, let's just replace the value. It's a mu naught by 4 pi into I multiplied by 2 pi r square. Yes, this was 2 was there and 2 pi r has been multiplied. It's a 2 pi r square divided by 4 pi into r cube. So if I arrange it correctly, it's a mu naught by 4 pi multiplied by I multiplied by 2 pi r square, replacing the value of r, which is equals to root of r square plus x square, that would be equals to r square plus x square to the power 3 by 2. So let's have a look the formula very carefully, that this is the ring, this is its center. Let's suppose current I is flowing in this manner. This is the radius of the ring and this is the axis on which magnetic field is required. This is point P. So as we have derived it, that magnetic field at point P should be written as mu naught by 4 pi multiplied by I multiplied by 2 pi r square divided by r square plus x square to the power 3 by 2. Even this can be written as, this is 2 pi, this is 4 pi, this is 2. So that could be written as mu naught into IR square divided by 2 into bracket R square plus x square to the power 3 by 2, where where r is the radius of ring and perpendicular x is the perpendicular distance from the center of ring to point P. Is it clear? Is it clear? Yes. So this is the magnetic field due to charged circular ring on its axis. Now let's just observe and let's just derive all the necessary formulas based on this only. That let's discuss all cases that this was the situation. This was the ring. This is its center. This is R and this is X. My formula for this is B is equals to mu naught I R square divided by 2 into bracket R square plus X square to the power 3 by 2. Now very first case that if x equals to 0, that means magnetic field at the center, that if I required a magnetic field due to charge arc at the center, then what would be the value? So let's just look at this, put up the formula and try to get it done. It's a B is equals to mu naught I R square divide by 2 into bracket R square to the power x is 0, so this is 3 by 2. Now this is equals to mu naught I R square divide by this is square, this is cube, this 2 has been gone and this is equals to 2r cube. So this r square, this r cube, this is equals to mu naught I divide by 2r. This is magnetic field P. I hope this is clear. Is it clear? Is it clear? Great. This is very important for us. Very important. Yes, please do remember things. Yes, we are going to discuss all the parameters and then we will come back to this. Next. Let's suppose assume that if x is much less than r, that means you want to observe a location, something like this, that this is r and this is x. Yes, you want to observe a magnetic field at very close to the circular ring. So what would be the situation? Let's have a look. So what I can write is that B is equals to mu naught I by 2 into R into bracket 1 plus x square by r square to the power minus of 3 by 2. Is it clear? Yes, I am using the principle yes, of maths, so that it's a binomial expansion. It's a 1 plus x to the power n. If 1 is much less than x, I can write like this, it's a 1 plus n x, and I'm doing the same thing. Yes, so this is my n to the power minus of 3 by 2, and this could be written as mu naught I by 2r into bracket 1 minus 3 by 2 into bracket x square divided by r square. I hope this is clear. Yes, this is clear. Yes, so this is the point. If I want to observe it very close to the ring. Now let's look the different scenario. That let's suppose this is ring, this is its center, this is radius r, and this is a point P, this is x, and it's a third case. If x is much less than r, it is very far from the ring. So what would be the situation? So my magnetic field was, it's a mu naught IR square upon 2 into bracket r square plus x square to the power 3 by 2, as x is much greater than r. So I could write like this, it's a mu naught into I r square divided by 2 into bracket r square plus x square. But as x is much greater than r, there is no significance to adding r to it. So approximately I can write like this, it's a x cube. So this is equals to mu naught I r square upon 2 into x cube. Yes, even this could be represented as it's a mu naught by 4 pi, because I have multiplied a term by 2 pi multiplied by I multiplied by 2 pi r square divided by x cube. Yes, this is having a significance. Yes, but as at this point of time you can keep it this. I hope this is clear. Is it? Is it clear? Yes. And magnetic field last magnetic field due to charged arc. Magnetic field due to charged arc at its center. It is something like this. Yes, this is charged arc. This is point P. This is its radius r. Current flowing through this arc is I, and this is theta. So for magnetic field at point P, I can write like this, it's a mu naught I by 2r multiplied by theta by 2 pi. It's a magnetic field at point P that could be written as mu naught I by 2r multiplied by theta by 2 pi. That's it. Yes. What about the direction? Direction of magnetic field at point P. First, if current is in clockwise direction, then magnetic field at P is inside the plane. And if current is in anti-clockwise direction, then magnetic field at P is outside the plane. Yes, so if it is clockwise, it should be inside the plane. If it is outside the plane, it is outside the plane. Yes, it is the same thing. It is the same thing that we have used for the wires, that we make it imaginary loop and that all stuff. Yes, this is the same thing. So I hope this is clear. Is it clear? Is it? Yes, this is the master formula using which you are going to derive each and everything. You can derive it everything. Yes, but on the center. Yes, so let's look for the questions. It is something like this, that this is 30 degree, current I is flowing, this is radius r, this is point P. What do they want? They want that find magnetic field at point P. You want this. It's a find magnetic field at point P. So what you are supposed to do is, it's a BP, that is equals to mu naught I by 2r multiplied by theta by 2 pi. I hope this is clear. Is it? Great. So this is equals to mu naught I by 2r into theta by 2 pi. This is mu naught I by 2r multiplied by theta. Theta is the 30 degree, 30. So 30 degree can be represented as pi by 6. Yes, I hope you understand. Pi is 180 degree. So 180 by 6, which is a 30. So 30 pi by 6. This is equals to pi by 6 into 1 by 2 pi. This pi has gone, and this is equals to mu naught I by 2 2s are 4, 4 6 are 24. It's a 24 hour. Yes, now time for the direction. As you can see, it is current is moving in the clockwise direction, so use your right hand. Use your right hand and curl your fingers in the direction of current. Curl your fingers in the direction of current. Then the fingers will give the direction of current, while thumb will give the direction of magnetic field. Shall I write this? Shall I? Let's have a look. That if you curl your right hand fingers in the direction of current, then thumb will give direction of field. Yes, here we are talking about the magnetic field, that you understand. So as current is moving in clockwise direction, it should be inside the plane. I hope you understand this. Is it? Is it a bit easier? Yes. So let's work for the next question. Do it quickly. Now have your pen and paper with you guys. Please do it as fast as you can do it. This is circular charge duct. Something like this. This is 45 degree. Through this a current of I is flowing. Through this current of 2I is flowing. This is of radius R, and this distance is again R. This is point P. What do you want? You want that find magnetic field at point P. So what you need to do is, let's just give them a number. That this is first wire, this is second arc, this is first arc, this is second arc. What you need to do is you need to write down only the magnetic field due to both, find out the direction, and use vectors law of algebra to get it done. Yes, so let's take a first step to find out the magnitude. Master formula, it's a mu naught I by 2r multiplied by theta by 2 pi. So that could be written as mu naught I by 2r multiplied by theta. Here the theta, it's an angle, it's a 45 degree. So this is equals to pi by 4 into 1 by 2 pi. This 2 pi and this 2 pi has gone. So this is equals to mu naught I divided by 2, 2s are 4, 4 4s are 16, it's a 16r. It's a B1. Now let's talk about the B2. Yes, so this is mu naught multiplied by as current is 2I, divide by 2 into radius is r, multiplied by theta, it's a pi by 4 into 1 by 2 pi. I hope this is clear. This pi has gone, and the term that remains, this 2 has gone. This is 2 4s are 8. So this is mu naught I by 8r. But one moment. Here, from here to here, the separation is, this is r, again this is r. So this separation should be 2r. So this r should be replaced by 2r. So this is 2r multiplied by 2. So this is 2 2s are 4, 4 4s are 16, 16 2s are 32. So this is 32r. That should be a 32r. One moment. Yes, So this is mu naught I by 8r, and this is mu naught I by 32r. So now let's find out the direction. A fast arc current is flowing in the clockwise direction. So use your right hand, yes, and curl your fingers of right hand in the direction of current. Then the thumb will represent the direction of magnetic field. So have you did it? Have you? Where your thumb is pointing? Yes, it is inside the plane. So as it is inside the plane, it should be in inside the plane. And where the second arc, thumb of the second arc is pointing, yes, it is outside the plane. So as it is outside the plane, this should be represented as dot. So B net could be written as B1 minus of B2, or it could be B2 minus of B1. Yes, so it's a mu naught I by 32R minus of 4 mu naught I by 32R. That could be written as 1 minus 4. It's a minus of 3 by 32 into mu naught I by R. I hope this is clear. So net magnetic field will be outside the plane. Net magnetic field will be outside the plane. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. So let's work for the next question. The situation is that this is circular arc and current flowing is I. This radius is R. You want a magnetic field at this point. So find magnetic field at point P. This is the requirement. So what I need to do is that B should be is equals to mu naught I by 2R into theta by 2 pi. In this case, as it is a circular charged arc, it's a complete circle. So my theta would be equals to 2 pi. Yes. So this is equals to mu naught I by 2R multiplied by 2 pi by 2 pi. And that should be is equals to mu naught I by 2R. I hope this is clear. As you can see this, that current is flowing in the anti-clockwise direction. So arrange your right hand and curl your right hand fingers such that it will represent the direction of current. Then the thumb will represent the direction of magnetic field. Yes, it is outside the plane. That's it. It's a mu naught I by 2R. I hope this is clear. Is it? Is it clear? Is it? Are you sure? Can we move for the second question? Can we? Okay, great. Let's have a look. Let's suppose this is circle and another concentric circle. Yes, the radius of the first one, it's an R. The radius of the second one, it's a 2R. Current, it's an I. Here current, it's again I. At a center point P is there, and you require magnetic field at point P. So how can you do this? So let's just give them a number, that this is the first, this is the second. So magnetic field due to first, it's a mu naught I by 2R. This is my standard relation. Yes, so as even current flowing is I, radius is R, so this is the relation. It's a B at magnetic field point P is the mu naught I by 2 into R. Now let's work for the second. It's a mu naught I by 2 into R, but the radius is 2R, so this is 2 into 2R. That should be represented as mu naught I by 4R. I hope this is clear. Now let's work for the direction. As this current is flowing in anticlockwise direction, so its magnetic field will be outside the plane. Even in the second loop, the current flowing is outside, is in anticlockwise direction, and as it is flowing in the anticlockwise direction of magnetic field will be outside the plane. So B net will be equals to, both are having the same direction. that would be equals to edit. It's a b1 plus b2. So this is equals to mu naught I by 2r plus mu naught I by 4r. So this is equals to 2 2s are 4. It's 2 mu naught I by 4r plus mu naught I by 4r. It's a 2 plus 1. This is 3 by 4 mu naught I by r outside the plane. I hope this is clear. This is first, this is second. Is it clear? Is it got it? Any query? No? Ready for the next question? Yes, you are doing it well. So keep moving and keep working hard and do it fast. Let's suppose this is circular charged arc. When its radius is r, current that is of 2I. What do you want? You want that find magnetic field. Find magnetic field at point P. So it's BP, which is equals to mu naught I by 2r multiplied by theta by 2 pi. So that should be is equals to mu naught multiplied by I. That could be represented as 2I divided by 2 into r into theta. Yes, it is a arc having a pi as the angle. It's a pi by 2 pi. So this has been cancelled. Even this has been gone. And the term that remain is mu naught I by r. Now, where is it? Clockwise or anti-clockwise? Yes, current is flowing in the anti-clockwise direction. And as current is flowing in the anti-clockwise direction, it should be outside the plane. Something like this. I hope this is clear. Is it clear? Can we move for the next question? Can we? Great. Let's have a look. Let's suppose this is one of the circular arc here. It is something like this. The current is flowing in this fashion. This radius from here to here, it's a 2r. And from here to here, this inner circle, it's a radius of r. Current, it is of I. Point P, it is at here. So you want to find out magnetic field at point P. So what you need to do is that you must understand that how many segments are there for which you require a magnetic field. So if I mark those segments, this is the first segment. This wire, it's a second segment. This is third segment. And this wire is the fourth segment. So what you need to do is you need to write a magnetic field due to each and every segment. Then you need to go for the direction, and at the last you need to apply a laws of vector addition and get it done. I hope this is clear. So let's just find it out one by one, each and every segment. So let's just begin with this 2 and 4th wire. The 4th wire, it is something like this, and the point is here. For the second wire, a point is something like this. So in both the cases, if you observe it, let's suppose if you observe this, theta is equals to 0 degree that we have discussed in the previous class. So magnetic field due to second wire and magnetic field due to 4th wire would be 0. So yes, that journey has over. Yes. Now let's work for the magnetic field at point P due to first wire and due to second wire. So magnetic field at first wire, it's a mu naught I by 2r multiplied by theta by 2 pi. This is the journey. Yes, as it is a circular charged arc, a semicircle arc, it's a mu naught I by 2r, and this distance it is a 4r. it's 2 into 2r multiplied by theta, which is equals to pi by 2 pi. So this has been gone, and this is 2, 2s are 4, 4 2s are 8. This is equals to mu naught I by 8r. Yes, as it is moving in the anti-clockwise direction, the magnetic field is outside the plane. I hope this is clear. Is it? Great. Now let's work for the B3. For B3, it's a mu naught I by 2 into r multiplied by theta by 2 pi. Yes, here the current is I and radius is r itself. This theta is equals to pi. So this is equals to mu naught I by 2r multiplied by pi by 2 pi. It's a 1 by 2, which is equals to mu naught I by 2 to the 4r. It is outside the plane as current is flowing anti-clockwise direction. Now what do you need to do? You need to add this because both are having the same direction, and this 2 produces a 0 magnetic field. So this B net, that should be is equals to B1 plus B3. This is equals to 3 mu naught I by 8r outside the plane. That's it. You did it. I hope this is clear. Is it clear? Is it clear? Any issues on this? Anything? Anything? No? Great. So is it clear? Will it be possible to do it? Will it be? Are you able to do this? Are you sure? Are you sure? Great. Let's work for the next question. Let's suppose that this is circular ring. From here current is entering, from here current is leaving. This is the radius of the circle, and let's suppose 2I current is entering, 2I current is leaving. This is point P where magnetic field is required. So they ask that find out magnetic field at point P. This is the requirement, that find out magnetic field at point P. So how could you do this? How could you do this? What can be done? So if I understand this very carefully, then what I feel is that at this point current is going to distributed in two segments. Certain current will be flowing through this and another certain will be flowing through this, but as this are diametrically opposite point, this and this are the diametrically opposite point, so same current is going to be divided because resistance on both the sides will be the same. So this is I, even this must be I, as this has been distributed in two segments. It's a I and I. So let's denote it as a number. This is 1, this is 2, as this is 1 and this is 2, that means B1, it is equals to, you can see this as a semicircular charged arc. So this is equals to mu naught I by 2r multiplied by theta, which is equals to pi divided by 2 pi. This is equals to mu naught I by 4r. This is B1, and as in this current is flowing in clockwise direction, so magnetic field at 1 would be inside the plane. I hope this is clear. Now let's just work for the second magnetic field. It's a B2, which should be written as mu naught I by 2r multiplied by pi by 2 pi, and that should be is equals to mu naught I by 4r. As current is flowing in the anti-clockwise direction, it is outside the plane. Yes. Now work for the B net. This B net would be equals to, one magnetic field is inside the plane, another magnetic field which is outside the plane. So this B net could be written as B1 minus of B2, and this is equals to mu naught I by 4r, mu naught I by 4r. This is 0. What was your answer? What was it? What was your answer? This B net would be a 0. Did you have the same answer? Do you? Do you have the same answer? Are you sure? So, if you remember the previous class, then we have a certain instructions that if current entering equals to current leaving and theta is 0 degree. Yes, so look at this. If you extend this theta is 0, then B net will be equals to 0. This was we have discussed for the straight wires, finite or infinite length. It is the same thing. Here it is the same thing, but we are talking about the B net and we are not talking about the individual, because if they ask that, let's suppose give them a name, it's an A B, and this is segment as an x1 and this is segment as an x2. So what they can do is that they suppose ask that find out magnetic field for segment x1 or x2. Yes, they can ask this and there is nothing harm in that. Yes, so we must understand and we must keep in mind that due to this situation, that current entering that is of 2i, current leaving that is of 2i, so same amount of current is leaving the circuit as that amount of current is entering the circuit, and from where it is entering it makes an angle theta. From where it is entering it makes an angle theta, and that theta would be a 0 degree. So in this situation B net is 0. B net is 0. So sometime they tempt it that they are going to give us the same direction. We are in that much hurry that we are not reading, we are not going through the data, complete data, and we must understand that yes, this is the question which answer would be a 0. As we get tempt, they are going to put a first option as a 0, we are going to take it and it would be a -1. Yes, so please go through your data very carefully. Go through your data very carefully. This is essential. This is must, not even should. So please understood that they can ask this, and magnetic field due to segment, any of the segment, it would be a, you can understand that it could be for x1, it could be for x2 and something like this. At that point of time magnetic field will not be a 0, it is certain finite numbers. Is it clear? Is it one? Great. Now let's work for the next question, what it is. So the situation given is something like this. This is the center, this is the center, and this is point P. Let's say from here current is entering, that is of 4i, and from here current is leaving, this is 4i. What do you want? You want that find magnetic field at point P. Yes, so what you understand using this is first 4i entering, 4i leaving. Yes, so this is the current that enters, this is the current that left, and where it is entering, this theta is equals to 0 degree, so B at P would be equals to 0. I hope you can do with this. Yes, yes, so the net magnetic field at point P in this situation is 0. Is it done? Is it done? Are you sure? Okay, great. So if you are done with this, if you are done with this, now let's understood one more situation, that suppose this segment is of x1, this segment is of x2, and they want that find magnetic field due to segment x1 and segment x2. Yes, you need to find it. So what you are supposed to do is, now take your time of 40 seconds, distribute the current, and tell me how could we do this. Do it fast, very quickly. Can you do it? Can you? Can you? Yes, time up. So have you did it? Yes, how should I do this? Let's divide your complete ring into four segments. Yes, first, second, third, and fourth. Let's assume each segment, that means each wire of quarter, has a resistance of R. So as 4I current is entering, so here the resistance is R, R, R. So on this side the 3R would be the resistance, and on this side the resistance would be R. It is something like this, that 4I current is entering the circuit. Here the resistance is 3R, here the resistance is R, and this 4I is leaving. So when I distribute the currents, yes, it's a I current that has been passed through this, it's a 3I current that has been passed through this. So now what you need to do is, let's write down the magnetic field due to x1, it's a B due to x1, this is equals to mu naught I by 2R multiplied by theta by 2 pi. So this is equals to mu naught into x1. The x1 segment is having a current of 3I divided by 2 into R multiplied by theta. Yes, you can see this, it's a 90-degree arc. So 90 degree, it's a pi by 2 multiplied by 1 by 2 pi. So let's just try to get it solved. It's a pi that has been gone, and this is equals to 3 mu naught I divided by 2, 2s are 4, 4 2s are 8, it's an 8R. It's a 3 mu naught I divided by 8R, and this current, as you can see, this current is moving in anti-clockwise direction, and this through this segment the current will be moving in clockwise direction. So for the x1 segment, as current is moving in anti-clockwise direction, magnetic field will be outside. Magnetic field will be the outside. Yes. Now let's work for the magnetic field due to second segment. It's a magnetic field due to x2. So it's a bx2, that is equals to mu naught I by 2R multiplied by theta by 2 pi. So current here, it's a I divided by 2 into R multiplied by theta. This is 90, 90, 90. It's a 180 plus 90, 270, and 270 could be written as 3 pi by 2. It's 3 pi by 2 multiplied by 1 by 2 pi. This has gone. So this is equals to 3 mu naught I divided by 2 2s are 4, 4 2s are 8. It's a 8R, and this is in the clockwise direction. As you can observe this, due to first segment it is outside the plane, due to second segment it is inside the plane. So B net is 0. Our decision was correct, and this is even the magnetic field due to the segment x1 and due to the segment x2. Is it clear? Is it clear? So always remember this thing, the amount of current that is entering the circuit and amount of current that is leaving the circuit, both are the same. If this is the task, then and theta which makes when it enters and theta which makes when it leaves the circuit, is 0. If this both conditions are satisfied, if this both conditions are satisfied, then net magnetic field at the center, then net magnetic field at that point would be a 0. Is it clear? Is it any doubts in this? Any doubts in this? Anything? Are you sure? Are you? Great. So let's work for the next question. Let's suppose this is circular charge dark, and these two are the diametrically opposite point. This is point A, this is point B, and let's assume that certain current I is entering and certain current I is leaving. This is point B. Yes, but now there is certain change in the situation, that this part has been kept in the ice cubes. These are the ice cubes. Now what do you want? You want that find out direction of magnetic field for the situation shown in figure. Yes, these are the ice cubes. And when I say it's an ice cube, let's understood that they are at theta, or the temperature at 0 degrees Celsius. They are the ice cubes at 0 degrees Celsius. So, and you want to find out the direction of magnetic field for the situation shown in figure. So what you can do, for this, again think for the 30 seconds. Do it now and do it fast. Yes, what are you thinking? What can be done? What can be done? What I understood is that this I must be divided, and this I must be divided into two currents. It's an I1, it's a I1 from here and I2 from here. Now only the question is, does I1 and I2 will be equal? Does I1 and I2 will be equal? So if you understand this, this is the ring that has been made up from the conductor, and in the third unit, current electricity, we have learned this, that for metals, resistance increases as temperature increases. Yes, this is what we have learned in the third unit, current electricity. So now in this situation, let's look at this. The lower segment, that is of I2 segments, has been kept at 0 degrees Celsius, and this segment has been kept at the room temperature, which must be obvious then that it is greater than 0 degrees Celsius. So this is R1, it's a resistance 1 of this segment, it is a resistance 2 of this segment. So as I could understood that R1 must be greater than R2, resistance of first segment, because it is at higher temperature, resistance of first segment must be greater than the resistance of the second segment. And if resistance is higher, that means your current should be less than this. So current through I1 would be current through first segment would be less than the current through the second segment. So I1 must be less than I2. Now let's write it down, the B1 and B2. The B1 is equals to mu naught I1 divided by 2R. B2, it's a mu naught I2 divided by 2R. Yes, the magnetic field due to first segment, as it is moving in the clockwise direction, it should be inside the plane. The magnetic field due to second, it is outside, so it is a dot. But as I understand that I1 is less than I2, or I2 is greater than I1, that means B2 is greater than B1. So B net will be outside the plane. I hope this is clear. I hope this is clear. Yes. Do you understand this? Do you understand this? Okay. Can you do the same kind of question? But it is for your purpose. Yes, that means you are going to do it. It's a try yourself kind of thing. Let's look at this. And this has been kept. This segment has been kept. In the boiling water. Yes. So current 2I is entering. Current 2I is leaving. This is the first segment. This is the second segment. And what do you want? This is point P. Find out direction of magnetic field at point P. This is the situation that you need to find out the direction. You need to find out the direction of magnetic field at point P. Yes, I hope you can do this. It's do yourself. So can you do this? Can you? I'm sure you will be. Great. Let's work for the next question. Let's work for it. So this question is let's suppose that this is a circle which carries a current of 2I in this fashion, and this is its radius R. Now, and here it's a point P. Here a infinite wire is passing, and this is the current I, and this distance is of 4R. So now find out magnetic field. Find out magnetic field at point P. This is our requirement, that I need to find out. I need to find out magnetic field at point P. So how should I do this? How should I do this? So what I understood is that you need to find out magnetic field due to both the sections. That means that this is my first section, it's a circular ring, and this infinite wire, it is the second one. So let's just get it done. B1, it's a mu naught into I, it's a 2I divided by 2 into R. It's a mu naught into I divided by 2 into R. So this is equals to mu naught I divided by R. And the second one, it's a B2, which should be is equals to, this is infinite wire. As it is an infinite wire, it's a mu naught I by 2 pi R. This is equals to mu naught I divided by 2 pi multiplied by distance. Yes, this distance is of 4R. So this is an actual It's a mu naught I by 8 pi r. Now let's work for the directions. That as current is flowing in the anti-clockwise direction, so the magnetic field due to this current segment is in the outside the plane. And as you can see this, that current due to a straight infinite length wire, yes, using the right hand palm rule, what it is, how you remember it? What? Did you forget it? Do you? No? Great. So right hand palm rule, that you need to arrange your right hand palm such that your thumb will point out the direction of current, and you need to stretch your fingers towards the point where magnetic field is required. So have you did it? Great. So now palm of your right hand will represent the direction of magnetic field. Yes, where is it? Where is it? Yes, it is the outside the plane. So this is the outside the plane. So B net, could be written as, I am going to add this because both are outside the plane. As both are outside the plane, that should be is equals to B1 plus B2. So this is equals to mu naught I by R plus mu naught I divided by 8 pi R. So this is equals to mu naught I by R into bracket 1 plus 1 by 8 pi, and that should be mu naught I by R into bracket 8 pi plus 1 divided by 8 pi. And this magnetic field is outside the plane. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's just wind it up this session over here. Yes. And we were discussing the magnetic field due to charged arc or the circular ring. Yes. So what you need to do is just practice a lot this kind of questions. Yes. In the next session, when we are going to tune in, we are going to discuss the questions that have hybrid applications. When I say hybrid application, that means it is having a wire, it is having a circular ring, and we are going to use it and we are going to solve this. I hope this is clear. So please do as many questions as possible. As when I begin the Biot-Savart law and their applications, I have told you that no paper could be find out such that there is no Biot-Savart law or their application has been asked. So no paper would be there which is not having this kind of questions. Every paper must ask this kind of questions. So please do it very carefully. Do as many questions as possible. Thank you. Have a good day. Take care. Bye bye.